Hello and welcome to our video solution for problem 4 from our first super quiz. And here what we are given is a whole bunch of rules or relations, if you like, from different domains, different codomains, and we want to determine whether or not they actually form functions, are injective, surjective, bijective, or possibly none of the above. So the first one is the rule whose domain and codomain are both the real numbers. And it's going to send each real number to its 7th power. So the first thing we want to check is, does this make sense in terms of the domain and the codomain? Right? So we can certainly take numbers from the reals and raise them to 7th powers. Right? So every real number has a 7th power. Right? And it's a unique 7th power, right? So I could even add this in here, right? A unique 7th power. And so this makes sense as a function, right? And not only is it a 7th power, but it's a 7th power in the reals, right? The 7th power of any real number is a real number. So we are perfectly good with the rule being a function. All right, now the question is the rule injective? So injective means that if you take any two, or if you take any real number, right? Think about it as coming from the codomain, that it comes from a unique real number or not at all. All right. Now, it turns out, of course, that if x is a real number, then the 7th root of x, we can define that. Whether x is positive, negative, 0, there exists a unique 7th root of x. Right? So this is uniquely defined. Okay, this by the way, would be different if we were working over the complex numbers, where if you have a real number, non-zero, say, there will actually possibly be more 7th roots. In fact, probably 7 7th roots. And so then the rule would not be injective. But over the real numbers, it's uniquely defined. And so again, we have not only just a function, but we have an injective function. Okay, next is this a surjective rule? And the answer, again, is going to be yes, because as we are seeing here, right, every real number has a 7th root. Right? So this statement here actually gives us both injectivity and surjectivity. So if you have some real number, x, and you say, well, what maps to it? And you say, well, you take the 7th root of x. And when you raise that to the 7th power, that will actually give you x. So we also have a surjective function. Okay, and of course, once you know that your function is both injective and surjective, well, that's the definition of being bijective. So we get this as well. Of course, we'll cross off e. From a graphical point of view, this isn't that hard to see. The graph of x to the 7th is very similar to the graph of, say, like y equals x cubed. Only it gets a lot flatter near 0. So very, very flat around here. And then it's going to pop up. And you can see, right, as x goes to infinity, the x to the 7th is also going to infinity. And as x goes to negative infinity, x to the 7th is going to negative infinity, and of course by the intermediate value theorem you're going to hit all of the points in between. So that gives you that surjectivity, and the uniqueness of the 7th root is giving you the injectivity. Okay, let's try number 2. So on number 2, it looks almost identical, only we're now raising the real number x to the 6th power. Of course, we can still do that, stay inside the real numbers, so there's no question about whether or not this will be a function. So that's okay. Of course, that immediately is going to rule out e. Now we want to know whether the rule is injective. So let's take something like, how about the number 1? How many numbers can we raise to the 6th power and get the number 1? And I claim, actually, there's going to be 2 of them. You can raise 1 to the 6th power, and that will get you 1. But you can also raise negative 1 to the 6th power, and that is going to give you 1. Which means we have a collision at 1, right? There are 2 different inputs which give you the same output, right? Or if you like, from the codomain side, I have one dot, and there are two arrows going into it. So this tells me the function is not injective. Of course, once it's not injective, it can't be bijective. All right, now we want to know whether the rule is surjective. And, well, one of the things we notice here, right, when we raise a negative number to the 6th power, we're getting a positive number. Of course, 0 raised to the 6th power will be 0. So we can get all of the non-negatives, but we can't get any of the negatives out. So x to the 6th is always greater than or equal to 0. And so this implies that the rule, right, so the rule is not surjective. Now, we could make it surjective if we change the codomain to be just the non-negative reals. So if we took the map x to the 6th, going from the reals to the non-negative reals, then this is surjective. But that's not what the problem asked for. The problem said from the reals to the reals, and so we do not get surjective here either. All right, let's check out number 3. In part 3, we are, well, I mean, it's kind of nice. We're describing this as a function already, so without doing any work, the problem is telling you it's a function. But what is it? Well, it's what we called the empty function in class. So this was a function here. Oh, look at that. Little typo. Nobody caught that during the exam. Too bad. From the empty set to a non-empty set. So we have a function going from the empty set to some non-empty set. Okay, and actually in class we showed that it doesn't even matter if this was the empty set or not. But so recall that what this means, right? If we go back to the definition of a function in terms of relations, right? So a relation from the empty set to the set S, right, is a subset of the Cartesian product. So a Cartesian product of the empty set with S. Now, a Cartesian product is going to be pairs of elements where you take something from the empty set and something from S, but there is nothing in the empty set. So this Cartesian product is just the empty set. There are no pairs. So we need a subset of the empty set. Okay, well, the empty set has only one subset, and that's itself. So the only subset of the empty set is the empty set. So this is the only possible relation from the empty set to S. Okay, is it a function? Right? Well, to be a function, you would need that for every element in the empty set, well, now it doesn't even matter what we say. There are no elements in the empty set. Whatever the conclusion is irrelevant because there's nothing to check in the hypothesis. Okay? So in fact, this is a function. Right? So the empty set is a function from the empty set to S. Okay, and that's what we call the empty function. Right? So this is called the empty function. Okay, and of course it is just the empty set, right? Because we can view all functions as sets. Okay, so it's the empty function. It is a function. Question, is it injective? Well, to be injective, we would need that for any element in S, there's at most one arrow going into it, right? That is, there's at most one pair where you have S in the second component and something in the first component. But we know that there are no pairs at all. So for every S and S, there's exactly 0 pairs with S in the second component. So for each S and S, there are no pairs of the form X comma S in the empty set. And so it is injective vacuously. Right? There are no pairs. And to be injective, you'd need there's at most one pair for each S. Okay, how about surjectivity? Well, since S is a non-empty set, and this is where being non-empty matters, since S is a non-empty set, we know there is at least one S in S. So if we let S be an element of S, well, then we know that there are no pairs. This is the same thing we just write. No pairs of the form X comma S in phi, right, or in the empty set. Well, what does that mean for surjectivity? Well, remember, for surjectivity, for each S in S, there must be at least one pair in your function, which has S in the second component. And so this rule is not surjective. If S had been the empty set, it would be. But for the non-empty set S, then it's not surjective. Of course, once we know it's not surjective, it's not bijective. And of course, because both A and B were true, we know that E is false. All right, on to number 4. In number 4, we have a rule which is going to go from the Cartesian product of the rational numbers and the rational numbers to the rational numbers. And the way it's going to work is it's going to take a pair of rational numbers, a over b comma c over d, and it's going to add the numerators, so you add a plus c, and it'll subtract the denominators. Of course, you can immediately see this is going to be a problem if b and d are equal to each other. And so there's a little condition, provided b is not equal to d. Now, in order for this to be a rule defined on all of q cross q, we need to say what happens if b and d are the same. And so we said, okay, if b is equal to d, then the rule will return 0 no matter what values were in the numerators, whatever the a and c are. All right, so first question is this rule a function? So to be a function, again, this means if you take one input, and remember one input here is a pair, it can't go to two different outputs. Now, one of the issues that we've seen with the rational numbers in class is that there are multiple representations for the same element. So, for example, the fraction 1/2 is the same as the fraction 2/4. It's the same as the fraction 3/6. So, let's try something, right? This is a great way to see that a function doesn't work when your domain contains things that have multiple representations. Is try two different representations for the same thing. So, for example, I might try here 1/2 comma, well, let's just make it as easy as possible. How about 1/1? Okay, 1/1 is a perfectly reasonable rational number. So this would map via the rule to, let's see, we add the numerators, so we get 1 plus 1. We don't need a parenthesis there, do we? Over, and we subtract 2 minus 1. So this would be 2/1. Okay, and that's the number 2. Let me try a different representation of a half, like, say, 2/4. And we can keep the same 1/1 there. So this will map to 2 plus 1 over 4 minus 1. Okay, well, 2 plus 1 is 3, 4 minus 1 is also 3, and 3/3 is 1. And these are not the same answers, right? 2 and 1 are not the same. So, but these two fractions, right, well, in the first component, they're the same, and even in the second component, so these two pairs are the same, but they're going to two different places. So diagrammatically, I would have one dot, right? Both of these represent the same dot, but they are now being mapped to two different dots, which means that this rule is not actually a function. Now, in the directions for the problem, we said, well, we can ask what it means, whether a rule, even if it's not a function, is injective. So, yeah, let's try it. Let's see, can you get the same outputs, right, by using different inputs? Well, we already have a couple here that we've computed, so maybe we can figure out another way of getting, say, a 1 out. So can we get 1 out in a different way? One thing we could do is just try to set it up so that it's going to work. So let's see here. Maybe I want to get, well, this would be the easiest way. Could I get 1/1 on the bottom? Let's see. Well, what if I put a 1 on the top and a 0 on the top? Okay, so this fraction is going to be 0. That's fine. And then on the bottom, I just need to make these differ by 1. So like I could choose 3 and 2. Okay, that works. So let's see. 1 plus 0 equals 1. 3 minus 2 is 1. And so sure enough, this map, which doesn't equal, it's going to get mapped to 1/1, which is 1. Okay, so again, diagrammatically, I now have this point 1, and it comes from two different places, right? One of them it comes from is the 2 over 4, comma 1 over 1, and one of them it comes from is the 1 over 3, 0 over 2. Now, you might say, well, that's a little bit hokey or dicey here, because this 2 over 4, 1 over 1 is also going to the 2. Well, that's true, right? Like, it goes somewhere else as well. But still, we can write it in this way, where these go to, this can go to two different things, but also this one is coming from two different things. In any case, okay, it's not injective, which of course immediately rules out it being bijective. All right, how about surjective? Can we get every possible rational number as an output? Well, let's see. So if I wanted to get some rational number, it's going to look like A over B. Okay, that's what an arbitrary one looks like. And so what I could do is take A in the first component and a 0 in the second component. And then, we got to be real careful here, right? What are we tempted to write? Well, we're tempted to just write that, and we get A plus 0 equals A, B plus 0, or B minus 0 equals B. But of course, we can't have a fraction with a 0 in the denominator. So what if we made this a 1, and we just add 1 to this B? So we now get B plus 1 minus 1. This will work almost all the time. Where is it going to be a problem? Well, what if B is equal to negative 1? So this will work if B is not equal to negative 1. If B is equal to negative 1, so if I have something like this, then I can still put the 0 there, but now I just want to get a B as the output. Of course, my B is negative 1. So let's see. If I want to get a negative 1, what could I do? Well, how about we'll just do, say, 2 and a 3 here. So 2 minus 3 is negative 1. A plus 0 is A. So we're able to do it. Okay. So yes, we're actually able to get any combination we like, and so we really will get a surjective rule here. Okay, number 5 coming. Okay, in number 5, we're given two sets S and T, and a rule says such that each element in S is mapped to exactly one element of T. So this should sound very familiar. We've talked about it already in this video. We're basically talking about the definition of a function. All right? So we're saying that if you draw this, say, diagrammatically, we have our S and we have our T. This says for each dot, right? So each element in S, it is mapped to something, and it's mapped to exactly one element. So there's one arrow coming out of each dot. And this is exactly what our definition of a function is. So absolutely, this rule is a function. Okay, but now in terms of it being injective or surjective, we really don't know, because it could be that a couple of these arrows went to the same place, right? This is totally a possibility. So if you have two different elements in S mapping to the same place, you don't have an injective function. So we just don't know. All right, so we cannot conclude that the rule is injective. Oops. Okay. Surjectivity, we have the same problem. We might have a dot which is left out. Just don't know. We don't have enough information, so we don't know that the rule is surjective. Of course, we can't then conclude that the rule is bijective. And we already know that it is a function, so none of the above doesn't work. All right, number 6, I believe, is our last one. So in number 6 here, we're actually given the rule diagrammatically, right? We're given two sets S and T. They each have 4 elements. And first question, is this actually a function? And looking down at the left, we notice there's not an arrow coming out of this dot here, which means we do not have a function. To have a function from S to T, we would need that for each element in S, there's exactly one T that it maps to. Well, here's an element in S, and there is no T that it maps to. So the rule is not a function. Is it injective? Well, let's see. We look at T, and we ask, is there at most one arrow going into each dot? And sure enough, there is. Right? We have 1, 1, 0, and 1. So yes, it is an injective rule. How about surjective? Well, we look again at the codomain and ask, is there at least one arrow going into each dot? Well, good on the first, good on the second. Oh, nothing going into the third. So no, it is not surjective, which means it is not bijective. And we did have one of these circled, so it's not going to be none of the above. All right. Hopefully this gives you enough fodder for understanding how these different definitions work.